Recording in progress.
Good morning, everyone. How are y'all doing today?
Morning.
It's a great looking Wednesday out there, isn't it? I hope we get some rain soon. We might get all the way through January with pretty much no rain. But I hear maybe some rain is in the forecast for next week. The rest of you doing good? Doing well, thank you. Well, how's your semester going so far? I know we're just getting started, but everything going smoothly? Got all your classes? Got signed up? Well, I hope we'll get a few more people in here. Looks like on Zoom we've got about 8 people. Usually I get about a quarter to a third of the students for this class. For this particular class, there's about 100 people signed up. Actually, probably a little bit less, probably closer to 80 to 90. And so I was kind of expecting we might get about between 15 and 20 people. But so far doing pretty good at about 8. I think last time we peaked out at about 15. Oh, we couldn't get into the wait list for physics. That's a bummer.
Yeah, I went yesterday. There's an 8 a.m. class, and there were supposed to be only 16 people as a cap, and 30 people showed up to the classroom.
Oh no. What'd they do?
Yeah, half the people there were just trying to get in from the wait list as well.
Did they let them in?
No, because they couldn't go above the cap because there was already the 16 people that got in was also there.
Oh, it probably has to do with the amount of equipment they have.
Yeah.
So was there another one you can get into?
No, physics 205 is the only one that had full. Every class is full.
Oh, man, that stinks.
I have a question. I just noticed that the binary, octal, and hex quiz, it said we should do it 30 minutes before class. Was that like a set in stone due date? Because I know you said you don't do due dates in this class.
No, but it's well, I had a slide just for you for this.
I apologize. I just didn't see that there was a
That's okay. We're still kind of
requirement to do that before the Zoom call.
Getting into the flow of things here. So the quizzes that I posted there are intended to be done before we have the live sessions. They're there,
Oh, okay.
They're there not to figure out whether you already know all the material. They're more like a tool to help you and I figure out what you got and didn't get out of the reading and what's still a little fuzzy and what's clear to you. So The quizzes are there just to help kind of focus your attention on what's important, help me understand where you're having trouble, and then if you do them before the live session, that would be great. Now, like I said, there's no set in stone due date, so you can still do them, but it's not mandatory, right?
Okay, I apologize. I'll get them completed in the future before Zoom calls.
And they're really short. They're like 6 to 10 questions, all based on the reading. And if you don't get all the questions right, It just means that maybe you have something that you don't quite understand yet. Take the quiz again, and you can just keep taking it as many times as you need in order to get all the questions. And that'll kind of give you a foundation of terminology and some concepts coming into here so that now you can ask some questions about things that you don't quite understand.
Okay.
All right. Well, I thought that I would start with a little, I'm going to turn off the music first. I thought I would start with a little kind of, kind of a magic trick, okay? So, let's see if I switch over here, and on the screen there, you should see a grid with a whole bunch of numbers. Actually, it's broken up into 6 blocks. And you can see the numbers span from 1 up into the 60s. And so what I want you to do is pick a number between 1 and 60 or so, and then find each one of those cards that has that number on it. So look in this one, look in this one, look in this one, look in the other 3. Find your number, and let's call this card A. This one is B, this is C, D, E, and F. So look at all those, find your number, and then post in the Zoom chat, or for people who are watching on YouTube, post in the YouTube chat, which card or cards does your number appear on? And then I'm going to try to guess your number. I'm not going to do any like fancy calculations. I haven't memorized a whole bunch of stuff. You just post which letters your number appears on, and then I will try to guess your number. Okay, well, so some stuff's already rolling in here. Let me look here at what we've got. So, Urbano, your number, I believe, is 26.
Yep.
All right. Let's see. Who else can I do here? Serhi, your number is 3. Did I get that? Yeah? It looks like Dar, your number is 19.
Yep.
All right. Cody, you're 36. Correct, he says. Serhi, you're 1. That one's easy. Jacob, I think you're 59. Yeah? All right. So far I'm doing pretty good. I haven't lost any yet.
I thought this was a computer class, not Psychic 101.
That's physics. Oh, let's see. Max, oh boy, yours is going to be tricky there because you're on, you got your numbers on 5 of the cards. So I really got to think about that one. Is it 31?
Yep, that's it.
Oh. And when I'm looking down here, all I'm doing is I'm looking at my iPad screen, the same thing that you see on your screen here. So I'm not like looking at a cheat sheet or anything like that. All right. So I think that's everyone. Does anyone know how I'm doing this? you think you know how you're doing this, just like post something in the chat that says, "I think I know how you're doing it," but don't tell us yet how you're doing it. And so I've picked a number. I've picked a number 25. Oh, sorry, I shouldn't. What am I doing here? That's crazy. Now I got to pick another number. I wasn't supposed to tell you the number. I was supposed to tell you what cards it appears on. So I got to pick another number. I've never done that before, where I was going to have you do it. So I'm picking a number here, and it appears on A, E, B, and C. A, E, B, and C. So A, B, C, and E. Can you figure out what my number is? A, B, C, and E. No, it's not 63. No, not 62. It's 30. Good. Cody's got it. It's 30. How'd you come up with that, Cody? Oh, not sure. Just guessed, huh? Well, I could try another one. Let's see. My number appears on A, B, C. That's it. Just A, B, and C. So now your eyes are darting back and forth, looking at A, B, and C, and trying to figure out which number appears on those three. It is 22. That's correct. How'd you get that?
I thought it was like prime numbers or even numbers, somewhere along that line.
Not quite. So here's how you do this little trick. Up in the top left-hand corner is a number. Four, 16, 2, 1, 8, and 32. When you told me what cards your numbers appeared on, I just looked at the numbers in the top left corner and I added them up. So the first time through, I had picked the number 30, and that one appears on A, B, C, and E. So you add up 4, 16, 2, and 8. And you get 30. The next number I picked was 22, which appears on A, B, and C. So you just add up 4, 16, and 2, and you get 22. And so, do you recognize those numbers? Those ones that are in the top left corner?
Powers of 2.
Yeah, those are the powers of 2. Maybe you...
all like the binary possibilities.
So we got 1, 2, 4, 8, 16, and 32. If my chosen number was 30, then I just need to find which numbers add up to 30. And So that would be 16 and 8, 4 and 2. And another number I picked was 22. So that would appear on 16 and 4 and 2. And if we pick one of the other numbers, let me flip back to this screen here and I'll pick another one, like 19. That would be on 16, 2, and 1. So with that particular set of numbers, any number that you can pick has a unique sum that adds up to it. There's no way to make some other set of those cards that would add up to the same number. So those are in fact just the powers of 2. You've probably seen them written out in the other order. So least number is on the right instead of on the left. And so this is how you can represent any given number in binary. If you want to convert a given number into its binary representation, which uses just zeros and ones, this is one way to do it. You just write out the powers of 2 across the top, starting with 1 on the right-hand side, and then increase by a multiple of 2 as you go towards the left. And if we just pick a number like 97, then we can use what I call the spending technique, which is you've got $97 to spend, and across the top are some prices of things that you can buy, and you want to spend all of your money. The only rule is you have to spend it on the most expensive thing first. So you've got $97 to spend. We can buy something for $128, but we don't have enough, so we can't buy anything there. We could buy something for $64, and the question then would be, how many things for $64 can we buy? Now, I can buy one thing for $64. What do I have left? So 97 minus 64, I believe that leaves 33 left over. So can I buy something for 32? I sure can. I can buy one thing. I've got $1 left over, and so I can't buy anything for 16, 8, 4, and 2, but I can buy one thing for $1, and now I've spent all of my money. So this is the binary representation of the number 97. Let's try another number. Let's do like 135. So I can spend $128. That leaves 7 left over. So nothing for 64, 32, or 16, or 8. But I can then spend $4 and leaves 3 left over. Then spend the remaining $3 on 2 and 1. Hope some of you did these kinds of conversions in your previous class, your Introduction to Computing class, or maybe your Introduction to Programming class. You learned how to convert between base 10, which is the number base that we're used to counting in, and binary, which is the number base that the computer works with natively. So you can do any number this way. Let's pick a bigger number. Let's do like 2022. So for that, we're going to need a few more digits. Let me write out some powers of 2 again. I'll start with 1, 2, 4, 8, 16, 32, 64, 128. You get pretty good at this after years and years of doing it. 256, 512, 1024, and 2048. But 2048 is too big, so I can really just stop at 1024. Okay, so I've got $2,022 to spend. Let me start by spending 1,024. And what does that leave left over? I need to get a calculator. I know, I don't have my computer set up so I can just do the calculation. So I got to do 2022 minus, whoops. Oh, I have $998 left over. So $998 left over. I can then spend 512. And I have 486 left over. So I can spend 256. And I have 230 left over. So I can spend 128. And now I have 102 left over. So I can spend 64. That leaves me with 38. So I can spend 32. That leaves me with 6. So no 16s, no 8s, but I can spend 4 and then 2 and then that's it. I'm all out of money. Okay, so that's one way of converting between base 10 and binary, base 2. You do this spending technique. You just write out the base 2s, powers of 2, across the top, and then you start with the left-hand side and try to spend all of your money, leaving nothing left over. So that's one way that you probably learned how to do the conversion. There's another way that you might have learned, and that's called repeated division. In this technique, you just repeatedly divide by your base. You divide by 2, coming up with a quotient and a remainder, and then you just continue dividing by 2 until you've got nothing left. So let's start with 97. We're going to divide that by 2, and that's going to give us 48 with a remainder of 1. You remember how to do this maybe from your early elementary school when you first started learning about division. You might not have known about fractions or decimals yet, so you did this remainder thing. Let's take the quotient, 48, and we'll divide that by 2. That gives us 24 with a remainder of 0. Then we'll do 24 divided by 2. That gives us 12 with a remainder of 0. 12 divided by 2 gives us 6 with a remainder of 0. 6 divided by 2 gives us 3, again with a remainder of 0. 3 divided by 2 is 1 with a remainder of 1. And then 1 divided by 2 is 0 with a remainder of 1. And then we're done because we've reached 0. So the answer is here in the remainders column. But we know from our previous slide over here that the answer is 11000001. Over here, here's the 11000001, so you have to read these answers going up. So when you're doing repeated division, you keep dividing by the base, in this case 2, until you reach 0, and then your answer is in the remainders, and you just read vertically going up. Let's try doing that again. 135 divided by 2 is 67 with a remainder of 1. 67 divided by 2 is 33 with a remainder of 1. 33 divided by 2 is 16 with a remainder of 1. 16 divided by 2 is 8 with a remainder of 0. 8 divided by 2 is 4 with a remainder of 0. 4 divided by 2 is 2 with a remainder of 0. 2 divided by 2 is 1 with a remainder of 0. And then 1 divided by 2 is 0 with a remainder of 1. And then our answer, as before, is over in the remainder column, and you just read upward. So that means that 135 in base 10 is equal to 1000111 in base 2. Now, some of these bits have names. This one over on the left-hand side, this is called the most significant bit, or MSB, because its value has the most significance. It has the greatest value towards the number. If I was to change that bit from a 1 to a 0, it would change the magnitude of the number by a lot. The one over on the right is called the least significant bit, or LSB. And its value changes the number by the least amount. So where in my column of remainders is the most significant bit, and where's the least significant bit? So where's the most significant bit? Is it at the top or at the bottom? You post in the chat your answer. It's a question for you. Where is it? Is it at the top or is it at the bottom? So where is the most significant bit? So the most significant bit is down here at the bottom. The least significant bit is up here at the top. So I've just shown you two techniques for converting between base 10 and base 2. One is the spending technique, and one is the repeated division technique. So which of those do you prefer? Neither one of them is better or worse, but which one do you prefer if you've had experience with both? I mean, which one looks like one that you could more naturally do yourself? Spending or repeated division? So you get a vote here for the spending one. I think for humans, like ourselves, the spending one works pretty well. It's very easy to arrive at the answer. You just have to do subtraction as you go along. I guess the biggest downside to doing the spending one is that sometimes, and this happens to me too, I forget to write down one of the powers of 2. Somewhere along the line, I just forget to write one of them and I skip over it. And then as I'm doing my spending, I get to the end and I have stuff left over. And I go, what happened there? Oh, I missed one of the powers of 2. And so the repeated division one is nice because you just keep dividing by 2 over and over again. Of course, you could make a mistake doing the division by 2. But I think the hardest part of the repeated division one is remembering to read your answer from the bottom going up. A lot of people read it from the top going down, and then the bits end up being reversed. However, which of those techniques do you think would be easier to write a program for? The repeated division one would be very easy to write a program for. All you have to do is write a loop that just keeps dividing by 2, computing the quotient and the remainder. And every time you get a remainder, which would be every time you do a division, you just append that onto a string and build up your sequence of zeros and ones. And you just keep doing that loop until your quotient reaches 0. So in your loop, you just do 2 operations. You do a divide to get the quotient, and then you do a modulo to get the remainder. You take the modulo, and actually you'll prepend it onto a string. You'll prepend means it goes up at the beginning, and the reason for that is it needs to be done in reverse order. And you keep repeating that until your quotient reaches 0. And then when you're done with that loop, you've got a string of zeros and ones that contains your binary string. So it's very easy for a computer to do the repeated division one. Okay, so that's binary. We've got a couple of techniques for converting between base 10 decimal and binary, or base 2. Binary is of course, the zeros and ones that the computer stores away in its memory. It's the basis for all the logic and the computations it does. But binary is not necessarily very useful for us as humans because the numbers that tend to be very long, it's kind of error prone for us humans to deal with binary. And so usually we humans deal with other number bases, more convenient ones. And some of these other number bases are things like hexadecimal, which is base 16, base 64, base 32. So a lot of those bases also happen to be powers of 2 as well. So let's take a look at hexadecimal, which is base 16. So in hexadecimal, and you've probably seen this already, there are 16 symbols. Decimal, the one that we use and have learned since childhood, uses 10 symbols, 0 through 9. Hexadecimal uses 16 symbols, 0 through 9, and then you just need 6 more symbols. And conventionally, we use letters of the alphabet. So the letter A stands in place for the value of 10. The letter B has a value 11. C has a value of 12, and up to F, which has a value of 15. And then in the center column here, I have written out the equivalent binary numbers, 0, 1, this is 2, this is 3, 4, and so forth, up to 18. And so actually, after F comes 1, 0. That's the hexadecimal number for 16, excuse me. 17 is 1, 1, 18 is 1, 2, and it counts from there. So actually counting in hexadecimal is just like counting in base 10, except that you go all the way up to F before you roll over to the next number. So in base 10, you go up through 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when you reach 10, what you're actually doing is you're looping the 9 back to a 0, and then you're bumping the next column up to 1. And then you go up to 19, you loop that 9 back to 0, and then you bump the next column up to 2. So in hexadecimal, you go from 0 up to F, and then you loop that back around to 0, and you bump the next column up by 1. So that's what we've done here. We went 0 to F, then we looped this back to 0, and then this went up to 1. So if we were to keep counting, it would go 1, 0, 1, 1, 1, 2, all the way up through 1, 9, then 1A, 1B, 1C, 1D, 1E, 1F, and then 2, 0. So again, that F would roll back to 0, and the next column would go up by 1. Okay, so hexadecimal is base 16. 16 symbols. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. And so we can convert numbers between base 10 and base 16 just as easily as we did it for binary. We can use both techniques. We can use the spending technique, and we can use the repeated division technique. Let's try doing 135 in base 10, and we're going to convert that to base 16. Let's use the spending technique. So we start out by writing the powers of 16. Start from the right-hand side. Start with 1. Then we multiply by 16. And then we multiply by 16 again. So we have 256, 16, and 1. And so this is 16 to the power of 0. This is 16 to the power of 1. And 16 to the power of 2. And then we just start spending. So I have $135 to spend. Can I buy anything for 256? No. Can I buy anything for 16? Sure. How many things can I buy for 16? Well, for binary, it was either 0 or 1. In base 16, it could be anywhere from 0 to 15 things. So again, we'll need our calculator. We need to figure out how many things can we buy for $16 if we have 135. And my calculator says 8. We can buy 8 things. But there's some money left over. So if I bought 8 things for $16, I would have spent $128, which means I've got 7 left over. So I can buy 7 things for $1, and now I'm done. Okay, spending method. Except that now the numbers aren't just 0 and 1, they're anywhere from 0 to 15. Let's try doing that using the repeated division. Let's do 135 divided by 16. That gives us 8 with a remainder of 7. And then we do 8 divided by 16. That gives us 0 with a remainder of 8. And just as before, the answers are in the remainder column, and we just read upward. So let's try doing it with 2022 in base 10. We can use the spending method. We've got 256, 16, and 1. How many things can we buy for $256? I can buy, according to my calculator, I can buy 7 things. So 2022 minus 256 times 7 is what I have left over. And let's see, let me run that calculation here. So 7 times 256. And then I'm going to subtract that from 2022. And I have 230 left over. So now I'm going to divide that by 16. And it says that I can buy 14 things for $16. And I have a remainder of 6 left over. So that means I can buy 6 things for $1. Okay, so there's my answer, 7, 14, and 6. However, the 14 needs to be converted into its equivalent hexadecimal representation. So all I got to do is look at this chart. I got to look for 14 over here on the left, and I can see that its equivalent value is E. So 7E6 in base 16 is my answer. So 2022 in base 10 is equal to 7E6 in base 16. That's what those little numbers on the right-hand side mean. That's the base that we're using. Okay, are we all good with that? So what good is base 16? Well, base 16 really is a more convenient way of representing binary. When you take a base 10 number and you convert it into binary, the number gets bigger. So you start with like a 2-digit base 10 number, and it becomes like anywhere from a 4 to an 8 bit number in base 2. It gets bigger. But when I go from base 10 to base 16, the number actually gets smaller. I can represent a bigger range of numbers using a fewer number of digits in hexadecimal. And the nice thing about hexadecimal is 16 is a power of 2. So again, if you look at this chart, I've got the first 16 hexadecimal numbers, and I also have the first 16 4-bit binary numbers. And these are all of the binary numbers in base 2 using 4 bits. So there are 16 numbers here, and that is all the combinations I can do using zeros and ones with just 4 bits. So what that means is that for every one hexadecimal digit, it can represent exactly 4 binary digits. And that gives me a really convenient way to convert between base 10 and base 16. So rather than doing the kind of tedious spending method or repeated division, I can just simply convert the number to binary, and I got a very fast way of doing it. And then from there, I can convert it to base 16 by just using groups of 4. So we already know that 2022 is 0. Well, we know that it's actually, let me just look back at the screen over here. Where is it? Here. It's 1, 2, 3, 4, 5, 6, 6 ones, and then 0, 0, 1, 1, 0. So let me just write that down over here. 6 ones, 1, 2, 3, 4, 5, 6, then 0, 0, 1, 1, 0. So I knew that the conversion to binary for 2022 was this particular string, and then all I have to do is group it into groups of 4, starting from the right. So here's a group of 4, here's a group of 4, and then there's one more group of 4 here, but I don't have enough digits, so I'll just add a 0 on in order to make it 4. I'll pad it out on the left with some extra zeros just to make it a nice group of 4. So once I've got these groups of 4, all I have to do is look in my chart for that particular bit sequence and then write down the equivalent hexadecimal number. So if I look for 0, 1, 1, 1, it is right here, and its equivalent number is 7. Then I look for 1, 1, 1, 0, which is right here, and its equivalent number is E. And then finally 0, 1, 1, 0 is right here, and its equivalent number is 6. So that went really fast. And this is why base 16 is kind of a more convenient way of writing binary out. So for a couple of reasons. One is the numbers get shorter, and the other is base 16 uses, each digit in base 16 uses exactly 4 bits. So if you put 2 of those together, you get 8 bits. That's a whole byte. So 2 hexadecimal digits can be used to represent 1 byte in the computer's memory. So 1 byte can hold a number between 0 and 255. It would require 8 bits to represent that number, but we can do it with just 2 hexadecimal digits. So a lot of programmers, when they're dealing with kind of low-level hardware issues and they want to talk about individual bits, they'll use hexadecimal instead because it's a really convenient way of representing binary. So before we move on, do we have any questions? Is this all kind of review for you? Or is this new stuff? Hang on, I gotta grab my laptop. Oh, it's pretty much review. Okay. That means we can move on and do some of the more fun stuff. All right, so is there anything beyond base 16? What would happen if we kept bumping up the base? It's all about the base, man, right? What would happen if we kept bumping that up? What would be the next one after 16? I know, 17, right? But what would sort of be the next sort of natural base that computer science people would use?
32.
32, yeah. So base 32. We need 32 symbols to do this. So obviously we have 0, 1, 2, 3, up to 9. And then we can start going into the letters. So we got A, B, C, D, E, F, G, H. And then how many letters, well, how many letters do we need and what letter do we end on? So we need 32 symbols. We've already used 10 of them for the numbers. So that leaves 22 left. There are 26 letters in the English alphabet, so we're not going to need all of them. Where do we end? What's the last letter? No, it's not P. We need to end on letter number 22.
V.
V, good. V is the last one. So their equivalent values are 0, 1, 2, 3, up to 9. A is worth 10. B is worth 11. C is worth 12. F is worth 15. G is worth 16. H is worth 17. And then V is worth 31. And that gives us a total of 32 symbols, numbered 0 through 31. So we can convert numbers from base 10 into base 32, just like we did with base 16 and base 2. We can use repeated division, we can use spending method. We just have to use 32 as the multiple instead of 16 or 2. So if we do 2022 and we divide by 32, we get 63 and something left over. I think we get a remainder of 5, but let me check on that. No, a remainder of 6. I was off by 1. So 63 divided by 32 is 1 with a remainder of 31. And then 31 divided by 32 is 0 with a remainder of, oh, no, sorry, not 31 divided by 32. This should be 0. Nope, that's even wrong too. 1. Sorry, I'm getting mixed up, right? So basically, you take your quotient, and that becomes this number here. And then you take the quotient, that becomes this number. And what I accidentally did is I took the remainder. So we get 0 with a remainder of 1. And so just like before, we're going to read this number going up. So we have 1, 31, and 6. But now we need to convert those into their equivalent base 32 numbers, which is 1V6. Which kind of sounds like a Fortnite endgame. So 2022 in base 10 is 1V6 in base 32. Ha, got your attention with that one, right? So is base 32 useful? Well, turns out not so much. But I'm using it as a stepping stone towards the next one, which is base 64. Okay, base 64, we need 64 symbols. And we're going to use letters and numbers just like we did before. We're going to do 0, 1, 2, 3, up to 9. And then we've got A, B, C. We'll go up to Z. And that gives us 36 symbols. And we still need more. So let's start using the lowercase letters. If we use all the lowercase letters, is that enough?
We only have 62.
So we're only at 62, so we need 2 more. And it turns out base 64 is actually a standard. So there's been a group of people that have agreed that in order to do base 64, you're going to use all the numbers, you're going to use all the uppercase letters, all the lowercase letters, and you're going to use plus and slash as your 2 remaining symbols. And that gives us a total of 64 symbols. Now it turns out in the standard, they're not in this order. They actually go uppercase letters, then lowercase letters, then the digits, then the plus and the slash. So conventionally we start with the digits, right? But in the base 64 standard, it's all flipped around. It's actually A through Z capital letters, then A through little z, then 0 to 9, and then plus and slash. And that gives us our total of 64. And 64 is a nice number. It's a base, it's a power of 2 number. 64 is equal to 2 to the 6. And so here's where I want you to kind of fit this into what we've been talking about. Base 16 is a nice base to talk about because it represents exactly 4 bits. 4 bits has a total of 16 combinations, and there are 16 digits in the hexadecimal counting system. Base 32 is 2 to the 5th. So each digit in base 32 represents 5 bits in binary. And then likewise, base 64 is 2 to the 6th. And so each hexadecimal, each base 64 character or digit represents 6 bits. So again, it can be a more compact way of representing binary numbers. Hexadecimal is really nice because 2 hexadecimal digits fills up exactly 8 bits or a byte. 64 characters equals 6 bits. That's not a nice multiple or factor of 8, but it turns out to be very useful for communicating between 2 devices. So a little bit of history. The internet has been around since the 1970s, so we're going on about 50 years. And the first thing that the internet was used for was really just sending messages back and forth between people using essentially email. Faster way of sending, because back then, if you wanted to send someone a message, you either called them up on the phone, and calling up on the phone was actually expensive back then. You could call someone in your local area, like in your city, usually for free. But if you wanted to make a call to another city, it cost money. Like, it could be like 10 cents per minute to talk to someone who was just in the next city over. That was called long distance calling. So anytime you had to leave your local phone company and transmit information or transmit your voice to another phone company in a different city, those 2 phone companies agreed that there would be a charge in order to use those valuable wires in between those 2 cities. And by valuable, I mean there was a limited number of them, and so by charging money, you could keep the usage down. And typically also, you would charge more money during the day and less money at night. So if you wanted to call someone in another city, it was to your advantage to wait until nighttime to make that call. And so the first email systems back in the 1970s and 1980s actually made phone calls between computer systems. The computers would actually call each other and transmit the information. They would send the bits down the phone line, and if you've heard old vintage style modems that make those screeching noises, those are basically the zeros and ones being sent back and forth between the two computers. So the nice thing about email was that you could transmit more information in less time. The bits would go out at 300 bits per second, or 1200 bits per second, or 2400 bits per second. That was state of the art back then. 2400 bits per second was really fast. But you could transmit an entire email message in just a few seconds, whereas if you wanted to call someone, it might take a few minutes to transmit that same information using your voice. So email became a faster way of transmitting small messages. And the computer system would usually wait until nighttime to actually do that transmission. So imagine sending an email to someone. Let's say you compose your email. It's going, up to another city, but it won't get sent until that night. So maybe you compose the email at 2 o'clock in the afternoon, and then sometime in the middle of the night, say around midnight or so, the email actually gets sent, and then the person who's receiving it doesn't get it until the next morning, when they actually come to the office, sit down, turn on their computer, and they look at their email. And again, you didn't have phones that you carried around in your pocket. You had to actually go to a computer, sit down, log into the computer, and then check your email there. Okay, so that's what sending email was like back in the 1970s and 1980s. But the key part of that is that email was a text-only medium, which is great if you just want to send text. You're just typing out a message and you want to send it to another person. But in the 1980s and 1990s, we started having computers with graphical displays. And you wanted to send a picture to someone. So a photograph, like a JPEG image or a GIF image, is composed of pixels. And those pixels each represent a color, a dot on your screen, which means you're no longer sending text. You're now sending picture, which is really just binary data. It's just ones and zeros. Every single pixel on that picture can be represented using just ones and zeros. So essentially, a picture is just a gigantic number. Every single pixel has a red, green, and blue component. Those red, green, and blues can each be represented using 8 bits. So one pixel is 24 bits of information. And that's just one pixel. And the next pixel is another 24 bits of information. So essentially, every single pixel is 3 bytes. So 3 bytes for the first pixel, 3 bytes for the next pixel, 3 bytes for the next pixel. And you can see that the number of bytes you have to send for an image is huge. Right? Even to send a little 100 by 100 pixel image, which is really small on a modern display, it's like a little postage stamp, is going to take up 10,000 pixels, or 30,000 bytes, which at 2400 bits per second would take a fair amount of time to send. And that's just for a little tiny picture. You know, if you want to send a decent sized picture, you now could be waiting a couple of minutes to send all the bits for that. And you've got another problem, right? Each one of those pixels can be represented by 3 bytes, and those 3 bytes could be anywhere from 0 to 255 in value. And so you're no longer sending text. You're now just sending raw binary information. And email was a text-only medium. It could only send typable characters. Characters that you can see on your keyboard were the only characters the email could contain. And back then, the internet was basically an ASCII-only medium as well. Unicode didn't exist yet. That didn't come about until the mid-90s or so. So emails had to consist of just typable ASCII characters, nothing else. How do you send a picture which can contain non-textual information through a medium that can only use textual information? And so the answer there is to take that binary information, those ones and zeros, and convert it into text. And that's where base 64 comes into play. Because the 64 symbols in the base 64 character set, which I've shown you here, are all typable characters. Letters, numbers, and a couple symbols. The next power of 2 up, base 128, we don't have enough symbols on the keyboard to represent 128 possible values. So 64 happens to be a nice power of 2 that holds all typable characters. There's some that aren't represented in that character set, but most of them are there. So if we can take a string of binary digits, bits, and convert them into text, then we can then send binary non-textual information using a medium that can only accommodate text. Okay, and so that's what base 64 is used for even today. If you want to send a picture to someone in an email message, what your email program will do, whether it's an app on your phone or the the Gmail website or Yahoo website that you use to actually compose that email message, once you attach that image to your email, it will convert all the pixel data in that image into just text in base 64. So base 64 is used to encode 8-bit data, images, sounds, movies, and so forth, into just 64 typable text characters. So if you were to look at an email message, and you can do this in most email programs, not the ones on your phone, but if you use like a desktop version of an email program, or even if you use something like Gmail, there's a menu somewhere in there that allows you to look at the raw message data. Not the one that's all nicely composed and has the images in it, but the actual raw data itself. And you'll see that an email consists of just typable text characters. Here's what one might look like right over here. This is just the top portion of it. So it starts out with what's called the header. And the header contains things like who it's from, the date that it was sent, the subject, who it's to, and then also some information about the fact that this email message contains multiple parts. So it contains a text portion, the portion that you see as text, and it also contains an image portion. So my text portion is pretty short, right? I just composed this to send a message to myself. So it says that, here's some text, here's an image, and then down here is the top portion of the image data. It comes with a file name, and it says that this is a base 64 encoding of the image. And then here's what it looks like. Now we got a comment here that sometimes you see this if you open a file in a text editor, but it's a file that wasn't intended to be looked at with a text editor. Yeah, sometimes you can do that. You can maybe open up a text editor and then drag an image onto it, and you might see something like this. So since the text, which can only display text, the text editor can't display the image, it then will convert it into something that you can see. It may not be that useful for you, but you can do it. So here's the email message. This is called the body of the message. Starts here and goes down. And then right here is the image data in base 64. Okay, so the way this works is it takes the pixel data of your image. Let me see if I can sketch out a little picture here. So here's the top left-hand corner of this image. And so each one of these pixels here is an RGB, or red, green, blue value, 3 bytes, which is 24 bits of information. And that's just one pixel, and the next pixel is also 3 bytes, the next pixel is 3 bytes, and so forth, all the way down the line. Now, I'm simplifying things a little bit. If this is something like a JPEG image, it's been compressed, which means the sequence of bytes or the sequence of bits don't necessarily map directly onto individual pixels, but the idea is the same. You've got some information which is not textual, and you want to convert it into a textual representation. So what we're going to do is we're going to take those 24 bits and lay them out in a line, and then we'll take the next 24 bits and lay those out in a line right next to it, and then the next 24 bits, lay them out in a line. And what we've got now is this gigantic binary number that contains millions or billions of individual bits. So it's a huge binary number. And then we just start doing repeated division or the spending method, and we convert it into base 64. Just divide by 64, get the quotient and the remainder. The remainder is going to be one of the base 64 characters. And then you just keep dividing and dividing and dividing until you get all the way through to a quotient of 0, and now you've got your base 64 representation of all those bits. Okay, so it's really just the same technique that I've been showing you for the last hour or so. You just do repeated division, and then you can, every time you get one of those remainders, you've got yourself a base 64 character, and that becomes your textual representation of that image. So the thing that I want to make really clear here is all we're doing is just changing representations. It's still the same image, right? We're just representing it using text rather than pixels. We're taking 24-bit quantities and we're turning them into, let's see, we have three 8-bit quantities making 24 bits, right? But each base 64 character is 6 bits. Right? So base 64 is 2 to the 6, remember that? So if I have 24 bits of information, which takes 3 bytes, I can represent those same 24 bits using 4 base 64 characters. Okay, did you get that? So I've got 8 bits here, 8 in here, 8 here, for a total of 24 bits. And then I can separate that into 6, 6, 6, and 6, making a total also of 24 bits. But now I'm using 4 base 64 characters instead of 3 8-bit characters. Okay, so every 3 bytes in my original data becomes 4 bytes in my base 64. And the question is, how does it know how to separate the pixels? Well, when we reverse the process, we get a big string of bits. Every 4 base 64 characters becomes 3 bytes. And then we just know every time we got a multiple of 4 base 64 numbers, we get 3 bytes out of that. Oh, and then the answer also is the program has to know how many bits each pixel is represented by. So in an image, there is usually going to be some information up at the front that tells you things like the dimensions of the image, width and height, and it also tells you information about how many bits per pixel are being used. Some images use 24 bits per pixel, some use 32, some use 16, some use 8. Depends upon the image format, and it also might depend upon how the image has been compressed to occupy less space. But the idea is still the same. We can take any arbitrary 24 bits, 3 bytes, and turn it into an equivalent 4-byte sequence of base 64. It doesn't matter whether it's an image or a sound or a movie. The whole point is to take non-textual binary data and turn it into something that can be sent in an email message. So does that mean your images get bigger when you send them through email? Yes, it absolutely does. It gets about 33% bigger. Does this also represent to the bit depth of color? Sure. So if you have like an HDR image, a high dynamic range image that uses more bits per pixel, 10 or 12 bits, it means that each pixel is now going to use 30 or 36 bits of information to represent a color there. And now your image basically just gets bigger. But still, you take all that pixel information, you just run them together as one continuous stream of bits, and then you just start dividing by 64, and every time you get a remainder, you've got yourself a base 64 character. Okay, so you can do this process with anything. Anything that can be represented in binary, which is basically anything in the computer. You can just run all the bits together and then start dividing by 64. Now, if you've got millions and millions of bits and you want to divide that by 64, you're going to come up with a quotient and a remainder, and that's a terrible process to do. So the computer has a fast way of converting to base 64, not by dividing, but by actually just sectioning it off into sections of 6 bits. And I gave you a little hint as to what that looks like over here when I wrote or drew this diagram here. Is you've got 24 bits, which you just lay out end to end, and you just section off every 6. It's kind of like converting to hexadecimal, but instead of using sections of 4 bits, you're now going to use 6. And you can do this to any data you want. It doesn't have to be an image or a sound. It could be anything you want. So here, for example, is converting. I want to convert the string hello, which is already textual data, but I want to convert this into base 64. So here's how the computer does it. First of all, it converts each letter or each character into its equivalent number. And here I just looked up the ASCII value of each one of these letters. So H is 72, E is 101, L is 108, and O is 111. And then just for the simplicity of converting that into binary, I also wrote down the hexadecimal equivalents of them. So 48 for H, 65 for E, 6C for L, and 6F for O. And then that made it easy to convert each one of these into binary because I just took the 4 and I converted it into 0100. That's 4 in binary. And then the 8 became 1000. Here's the 6 and the 5. Here's the 6 and the C, 6 and C, and then 6 and F. Okay, so I just wrote out the binary representation for HELLO. And again, one of the big points I want to make today is that each of these 4 representations, letters, decimal numbers, hexadecimal numbers, and binary, are all equivalent to each other. The letter H can be represented with the actual shape H that we recognize. It can be represented as a base 10 number. It can be represented as a base 16 number. And it can be represented as a base or a binary number. And those are all equivalent to each other. They're just different ways of looking at the same information. Okay? So if I want to convert this now into this binary sequence into base 64, all I got to do is just start sectioning off 6 bits at a time. So here's 6 bits. Oops. Here is 6 more. And then 6 there. And then 6 there. So my three 8-bit numbers became 4 base 64 numbers. And then I can just start looking up in this table that I've shown you on the screen here what each one of those sequence of 6 bits represents. So 010010, all I got to do is look in this table. 010010 0010. Let me see if I can find it. Here it is. 010010 is the letter S, capital letter. And then 000110. So 3 zeros and then 110 is right here. So it's the letter G. You can see how fast this would be for a computer. You just section it off into groups of 6, and then you just look in the table to see what each group of 6 represents. Next one, 010101. Oh, that's easy. 010101. Here it is. So that's the letter V. And then 101100. 101100. Here it is. It's the letter S, little s. Okay, and now we've got another group of 6 right here. And then another group of 6 right here. And then, we got 4 left over, but we need groups of 6. So here's what we're going to do, is we are going to pretend that there's 6 there. We're just going to add 2 more zeros to make a nice group of 6. This is called padding. Padding is extra data or extra bits that you add on to your main information in order to make it a nice even size. Okay, so now we've got groups of 6, and we just look at our table again. So we've got 011011, 011011, 011011. I think it's right here. This is B. This is it. And then 3 zeros, 110. 3 zeros. Here it is. It's capital G. And then finally we have 4 ones and 2 zeros. Here it is. 4 ones and 2 zeros is 8. So that is our base 64 representation of the 5 bytes that make up the 5 letters of the word hello. Notice that it got bigger. So the original text was 5 letters, and the base 64 representation was 7. Okay, there's one last thing going on here. If somebody was to receive this base 64 representation, and so what we would do is we would just send them the letters S, G, V, S, B, G, 8. We would just send those as ASCII characters. So it would actually send out more bits. And so what the receiver does is they just reverse the process. They take each one of the letters they received, they look in this table, and they construct, where's S? Here it is, they construct the equivalent bit sequence, and they just pack them all together. So they would construct the same bit sequence right here, and then they would just section it off into groups of 8, and then they would have their original bit sequence remaining, and then from that they could reverse that to the original text. So you just reverse the process. You take your base 64 encodings, you look in the table to see which each letter represents, you write down those bits, and then you just regroup them into groups of 8. So we have one little problem here, and that is we added on these extra 2 zeros as padding, but those are not part of the original data. And there's no way to know, for the recipient, to know whether these 2 bits were added on as padding or whether they were part of the original data and weren't padding at all. Because remember, the recipient doesn't really know that this is letters. It doesn't really know that these are bytes. It just knows that these are bits being sent to it. So this decoder doesn't know that whether these 2 bits are padding or if they were part of the original data. And so the base 64 standard says that if you add 2 bits of padding onto your bit stream, you put an equal sign, and this is a special symbol in base 64. The equal sign means that 2 bits of padding were added, and so the recipient should take 2 bits off in order to reclaim the original bits. It's also possible that 4 bits of padding were added. If that's the case, you put 2 equal signs on the end to indicate that 2 sets of 2 bits were added. And then those are the only 2 things you could add. You could add 2 bits or you could add 4 bits. You would never add 6 bits of padding because 6 bits just becomes a whole nother base 64 character. So you either have 2 bits of padding added or 4 bits of padding added. And so you either put 1 equal sign on the end or 2 equal signs on the end. And so just to show that this works, we can run the same text through a base 64 encoder, which you can get on the web pretty easily. This is a website called Crypty, and you can type in some text over here, and you can build a workflow, which I've already done here, to encode it through base 64, and then see what the equivalent text is over here. So if I type in hello on the left-hand side, we can see that we arrive at the same thing, SGV SBG8 equals. And I can also view this as bytes. So here's the equivalent hexadecimal representation. 53475673644738 and again, that is just a base 16 representation of base 64 representation. So it's all just converting one representation into another representation without changing the underlying information. Interestingly, I can also view it as punched tape. So punch tape uses 8 bits going vertically. These little dots here are just an alignment row, just to tell you whether you've got the tape facing this way or this way. But it's the same thing. It's just bits here. These are zeros and ones going down the line.
Yeah. May I ask a question?
Of course.
Just wondering, like, wouldn't the computer be, or wouldn't the program be able to tell, like, if there's 2 zeros at the end, wouldn't it be able to tell that those aren't lining up to a set of 8 bits?
Oh, that's a really good question. So the question was basically, if the data is going to be groups of 8 here, can't it just tell without this equal sign that 2 bits were added on? And yes, that's absolutely the case, right? You just stop at the group of 8 and you know that those extra 2 bits are sitting there dangling off the end, you can just throw them away. So the base 64 standard says you need to put those equal signs on there just first of all as kind of like a double check. Like, you know, if you're decoding it and suddenly, boom, you don't end up with a multiple of 8, it means you lost some information somewhere, and so you know the data was corrupted. So it works as kind of like a double check there. But another reason why you need to put that information on there is because if you had, and the people who were doing base 64 were like thinking ahead a little bit. They were like, well, you might actually want to take, let's say what I want to do is I want to send not one single image to my recipient, but 2 images to my recipient. And I'm just going to pack them back to back. Okay? So I'm going to have, you know, one set of image data here, and then right behind it, I'm going to have another set of image data. There's going to be no kind of like delimiter between the 2 of them. I'm just going to go back to back. Then those equal signs there let you know that one image is done and the next one is beginning. So that kind of like is a delimiter, right? So if I didn't have those equal signs there, then those characters would just get packed back to back, and then as I unpacked them, I would lose synchronization as I finished one image and went to the next one.
I see.
All right.
And you wouldn't, if they did happen to line up so that it did match up,
Yeah.
exactly, then it wouldn't matter because you're already starting the next image.
Right. And
at
remember,
the-
there's header
at that
information up at the
Okay.
front that says how big the image is, so you know how many
Right.
bytes to read in.
Okay.
Right. So that's what those padding characters are for, is just to act as kind of a delimiter to let you know this is the end of one and the beginning of the next. Okay, so getting back to kind of my big idea here is that you can take information, and let me distinguish between information and data. Data is just like raw bits, raw numbers, and information is raw numbers with a context. So for example, if I gave you the numbers like 72, 68, 75, 68, 73. And I just gave you those numbers. You wouldn't have any context about what those numbers mean. What could they be? They could be like characters, right? Those are all within the range of capital letters, so maybe those spell out a word. Or maybe those numbers represent some pixel information, the first couple of pixels in an image. Or maybe those characters represent an encrypted piece of information. So maybe I've done some kind of transformation to each one of those numbers, and without the key to how I did that transformation, you wouldn't know what those numbers represent. Or what those numbers might actually represent is the predicted high temperatures for the next 5 days. Without the context for what those numbers represent, you don't know what they mean. They could mean practically anything. And so the same thing is going on here. If I didn't tell you that once you decoded this base 64 string, that each one of those 8-bit sequences stands for a letter, you really just have to guess what they mean. Now, you might plug them into an ASCII character set and see that they happen to spell out a word, but you know, what if the word was in a foreign language? Or what if they were Unicode characters? In which case, those sequences of bits could represent foreign symbols. How would you know which one was correct? You wouldn't. And so that's the big idea here, is that all data that you put into the computer just gets turned into numbers. But you don't know what those numbers mean unless you also have contextual information with them. Otherwise, you just have to guess what they mean. And people use this to their advantage, and I'm going to wrap up with this here. People use this to their advantage, that I can take some information, strip away the contextual information about what it represents, and just end up with the raw data, just the numbers. And I can send that to a recipient. And if the recipient knows what that data represents, they can turn that back into information. But if a third party was to intercept those numbers, without that information about what it represents, they don't know what it represents, and they just have to guess. And there could be almost an infinite things it could represent. And so one of the things that I think is really cool and kind of spooky is there are spy agencies out there all over the world who are sending information to their agents using just radio waves, using radio transmitters and receivers that anyone could go to a department store and pick up a radio receiver, and you could listen in on these transmissions. And they're called number stations. They're just basically a radio transmitter out in the middle of nowhere, and they're just transmitting a sequence of numbers, usually 24 hours a day. But without information about what those numbers represent, they're just gobbledygook. Are they directives to go assassinate someone? Maybe. Are they information about where someone should go? Are they GPS coordinates? Maybe. Is it just random numbers sent to fool the enemy into thinking that it's information? Maybe. No one knows because no contextual information has been sent with it. So you can, if you want to, you can look up number stations. Let me see if I can bring this up here. Yeah, Wikipedia's got an article on this. And here's what they sound like. Let me see if we can bring this up. So this was a number station called the Lincolnshire Poacher. It always started out with this song called the Lincolnshire Poacher. But after the song was over, it would start reading off numbers.
0, 2, 5, 8, 8. 0, 2, 5, 8, 8.
And that would just repeat over and over again. So what do those numbers represent? 0, 2, 5, 8, 8. Well, without the context, who knows? Most likely what would happen is whoever was receiving those numbers had a book, a physical book, and they would just look at the book. Maybe they would turn to page 5, and on line number 88 would be the instructions for what to do. Or maybe in the book, it would say, just look up the number 5288, and there's a whole paragraph of text that represents, what you should do. Or maybe they're just random numbers, sent to thrown off the enemy off the trail. Who knows? But pretty much every country was using these up until just like a few decades ago. Once the internet took over and we were able to encrypt and decrypt information using just bits, number stations have kind of fallen by the wayside. But the nice thing about number stations, you can still find them out there. Get a shortwave radio receiver, look up on the internet for when and where to tune in, and you can listen in on these number stations. But without the code book that tells you what the numbers represent, you don't know what they are. So no one's ever been able to successfully decode these transmissions if they didn't have access to the key information, the book that would tell you what they mean. Here's another one.
9, 1, 2,
Speaking Russian.
8, 3, 9, 1, 2, 1, 0, 0, 8, 0, 1, 0, 0, 8, 0, 4, 6, 5, 4, 3, 4, 6, 5, 4, 3, 2, 5, 7, 2, 5, 7.
I'm going to pause that. So what do those numbers represent? Don't know. People are trying to figure it out. And you can find other things on the internet. They're called ARGs, alternative reality games, I think. And usually they consist of things like puzzles. You can, the most famous one is called Cicada 3301. And they lasted from 2011 to 2014. And what would happen is someone, whose identity is still unknown, would post an image on Twitter. I wonder if they're still there. No, I think this is someone else, so that's not them anymore. There used to be a nice website where they would go through the some of the puzzles. Anyway, what would happen is on Twitter they would send out an image, and it was just an image of, well, in this case it was a cicada, a bug, right? But hidden inside that image was some text, and you had to know to go look for it. And so the basic idea, I'm glossing over a lot of details here, but the basic idea was you took that image, and you know that every image is composed of red, green, and blue pixels, but if you were to just change the least significant bit of each pixel from a 0 to a 1 or a 1 to a 0, it would change the color of that pixel by an imperceptible amount. So visually, you wouldn't see any difference. But if you knew that the least significant bit of each pixel was actually a 1 or a 0, and you assembled 8 bits, 8 pixels into a byte, then you could get like a letter out of that. And then the next 8 pixels could represent another byte, and the next 8 pixels out of that could represent another byte. And if you knew to look for that particular sequence, you could then extract some data out of that image, which could be text. And that's exactly what Cicada 3301 did, was embed some text inside the pixels of an image. And if you knew to go and extract those pixels, you could extract that text. And that text contained further instructions on what to do next. And in some cases, it was a web address to go to, which would contain some more puzzles to solve. In some cases, it contained like actual GPS coordinates to go to. And if you went to those physical GPS coordinates, they were all over the world. And if you went there, there might be a telephone pole or a light pole sitting there, and taped to it was a poster containing like some more web addresses to go to, or some more numbers you had to decode. And so it was a puzzle. Then when you solved that puzzle, it led to another puzzle, and it led to another puzzle. And if you read all the folklore behind this Cicada 3301, you'll find it's very mysterious, right? All these people got together, they formed wiki pages, and they were chatting on things like Discord servers about what do these numbers mean, and they would start decoding it and writing down all the solutions. And part of this folklore is that a few people got all the way to the end. They had solved all the puzzles. And when they got to the end, they were contacted by someone and told, you're the kind of person we're looking for. You can solve these kinds of puzzles. We're looking for people that can solve these kinds of puzzles. And these people were never heard from again. It's like they were contacted by the CIA or MI6 or MI5 in the UK. They were looking for people who'd be good, like cryptographers and spies. And they were hired and never heard from again. So you can find these things out on the internet. These basically, you're just given a whole bunch of numbers, and you have to figure out what those numbers mean. So you try decoding them as ASCII, you try decoding them as Unicode. Maybe they're executable instructions. If you save them to a file, your program will run it as your computer will run it as a program. Maybe it's that. Maybe they're samples from a sound. You have to put it into a sound program and listen to the sound. Maybe, like I said, they're just pixels in an image, but only one of the bits out of each pixel is actually relevant to what you're looking for. Without the contextual information about what that data represents, you don't know what it means, and you just have to guess. And so that's kind of like the big idea I wanted you to get out today. I mean, certainly we learned about things like converting binary to decimal, and decimal to binary, and hexadecimal and base 64. But I wanted to show you that these are all just different ways of representing the same information. You've got text. You can represent it as numbers. You can represent them as bits. You can represent them as base 64. You can turn those letters into a sound. You can transform the data from one representation to another representation without changing the underlying data itself. And that's the big idea I want you to get across. That when you store data in a computer, it just becomes numbers. And those numbers can be represented in many different ways without changing the underlying data itself. Okay, I just blabbed at you for the last half hour. Do you have any final questions before we end the class for today? Eldar says, Lemino made a sick video about, was it about Cicada 3301 or was it about ARGs?
Cicada.
Cicada. And then someone on YouTube said, if you know Turkish, please check out our ARG. And then there's also some people on YouTube that are chatting back and forth what appears to me to be random characters. And I don't know if they're actually talking to themselves or if those are actually just random characters. And so again, without any contextual information, I don't know what those mean. So it's like someone saying VORRED, and someone else says VORNGO, VURFYI, VUM today. I don't know what those mean. Anything else? Okay, reminder. By Friday, this Friday, for those of you who are in my class, you should have made your initial posting for both the Introduce Yourself and the Case Against Grades discussions. By the following Monday, so 5 days from now, I want you to respond to at least 2 of your classmates. And then one final thing you should do is, after you've done those responses, wait another day or so, and then come back one more time to the discussion and see what people have posted about in response to your posting. Because in some cases, they've asked you some questions. And it's kind of like disappointing to ask a question and then not have it answered. So at minimum, you should make your posting, you should respond to 2 people, and then come back and see what the responses to your posting was and respond to them. Kind of like close the circle on the conversation so that people aren't just left dangling. And you might want to do that periodically over the next week or so. Just check back and see if someone has responded to you and see if there's a response that you could post. And then also, let's see. Oh, we're starting, so we've done binary transformations today. Binary, decimal, hexadecimal, base 64, base 32, and so forth. What we're starting into next week on Monday is we start talking about numbers. How do you represent numbers that aren't just whole numbers? On Monday, we'll talk about how do we represent negative numbers. We only have ones and zeros. We only have binary. How do we represent things like negative numbers using just ones and zeros? And then on Wednesday, we'll talk about how to represent floating point numbers. How do you represent numbers with a decimal portion of them? Again, using just ones and zeros. And then so next week, that'll complete our discussion of representing things in binary, representing numeric data in binary. And then we'll start getting into Boolean algebra, Boolean logic, gates and circuits, and that'll be a lot of fun too. So 2 weeks on the number stuff, and then I think another week or 2 weeks on the gates and logic circuits. Question is, where on Canvas are the Zoom recordings posted? If you look in the modules list, so when you log on to Canvas and you go into my class page, you'll be presented with just a single welcome page. That's only going to stay up for about another week or so. Once we get past the add drop period, I'm going to change that front page to just be the modules list. So when you log in, you'll just get the modules list for now. Just click on the modules link on the left-hand side, and you'll get the modules list. And each Zoom recording will be posted as an entry at the bottom of each module. So for the recording we're making today, it'll appear in the, I think it's the second module that has the information about information representation. So it'll say something like live stream, January 26th, and then a little information about what it's about. Click through to that and you'll get a link to both the Zoom recording and the YouTube recording. And I've made those pages editable. Anyone, including you, can click on edit and maybe add some notes to the bottom. And so if there were some interesting sections of the recording, you could put in something like a timestamp and a brief sentence or 2 about what that section is, so that people who are coming on later on can quickly jump to relevant sections of the recordings. So anyone can edit those pages and add some notes to the bottom. And it'd be great if we can kind of crowdsource. That was one of the feedbacks that I got last semester, was it was hard to jump through the recording to find the relevant sections. And so if somebody could, anytime you find a good section, like here's a section where he talked about converting binary to base 16. So write down the timestamp for that. Here's the section where we talked about base 64. Write down the timestamp for that. That'll help people to jump through the recordings fairly easily. Okay, good question. Last semester, I posted the videos as announcements, and so you got a little notification on your phone or in your email that an announcement had been posted. But this semester, I'm trying to just intersperse the videos in the modules themselves to make it easy to find the videos. Last time, if they were posted as announcements, you then had to figure out, okay, what day did he talk about that particular topic, and then go find the announcement from that section. Now I'm just posting them with the content itself. So that should make it easier to find the videos. And then by making the editable pages, it'll make it easier for people to find the relevant timestamps within the videos to go find what they're looking for. Okay? So I think next week there's a couple of quizzes to take. So there's one on signed integers. So take that one, ideally before Monday. And the textbook that I have is free. I talked to the professors that wrote it at Northeastern University, and they were kind enough to let me just use the textbook. But I don't have access to the original source document for that textbook. So there are some errors in the textbook, and I have no easy way of fixing them. So that's in part what the quizzes are about, is if you encounter something that seems confusing, it may be because there's actually a typo in the text. And then that's something that you can bring up with me, and then hopefully I've got some way of posting corrections to it. What I eventually want to do is eventually write my own version of that book that we use in this course, but that seems like something that's easier said than done. Okay, we don't have a lab session today. Normally on Wednesdays, starting at 11 o'clock, we would have a session where we would go over the programming assignment for the week, but we don't have one this week. A lot of students are still in flux. They're adding classes, dropping classes, so no programming assignment this week. But starting next week, we will have those. So what will happen is we'll end the quote-unquote lecture time at around 11 o'clock. We'll take a short break. The Zoom recording won't end. The YouTube recording won't end. We'll just take a break, and then we'll come back about 5 or 10 minutes later and then start going over the homework assignment. Oh, I feel like I'm just talking. So really, we're pretty much done, I think. I don't have anything extra for you. Any final questions?
No, not that I have. So have a nice day.
All right. Great. You too.
I actually got a lot of the, not specifics in here, but we went over binary and hexadecimal when I took assembly language at Chabot.
Mm-hmm.
And so a lot of this is pretty familiar.
Good.
And I'm enjoying seeing it again.
Great. Thanks. So hopefully we'll get into some new stuff pretty shortly. Now, if you took that assembly language class, you probably already did a little bit of logic gates and circuits.
Yeah,
you
did quite a lot of that actually.
Okay. So that'll be like I said maybe last time, this course is a survey of a lot of different topics, and you'll probably find connections between this course and other courses that you've taken. So, it's review for you, but it's also a connection, right?
Yeah.
And we're setting the foundation for being able to talk about other things that need the binary representations to be able to have a good discussion about them. Like when we get to cryptography, we're definitely going to need things like binary and hexadecimal and decimal to be able to turn data into numbers and then encrypt those numbers.
And that will be a very new course, a new section for me.
Oh, good. Something new. Good.
Yeah, I've seen that kind of stuff a bit, and I'm it's a bit beyond me right now, so I'm hoping hoping that'll be something I can learn.
The cryptography stuff?
Mm-hmm.
Yeah. That's a lot of fun, because it's actually really simple.
Mm-hmm.
But there's a lot of solid math going on behind it that makes it essentially unbreakable. But the actual computations are fairly simple. And it's a good thing they're simple because computers have to be able to do these calculations and they have to be doing them really fast.
Mm-hmm.
They just deal with really big numbers, really, really big numbers. So good. You'll get a lot of stuff out of this course. It'll be good.
Yep.
So review for now, and then we'll start getting into new stuff. Okay?
Cool.
All right. Well, have a good day, everyone. Sorry I ran over a bit. But it's a beautiful day out there. It's sunny.
I had something I wanted to say.
Yeah.
It's kind of just random, but I just kind of wanted to say thank you for all the effort you put into this online class, because I haven't had many other professors that have such good camera quality, recorded videos, and just all the effort that you put into it.
Oh, thanks.
So thank you.
You're welcome. I enjoy it. I tore down my whole home studio and reassembled it over the break. Actually, translation, I tore down my whole studio and reassembled it the week before class.
I can tell you a pretty cool background back there. Looks like you got like an oscilloscope or something.
Yep, I'll tell you more about that someday, right? But this is built explicitly. Once we went to like all online, I built that just for doing these live streams.
Nice, I like it.
So I'll tell you about all the stuff that's back there someday. There's an ancient Apple PC back there. Yep, right. You see it there?
Is it really?
Yeah, that's an old Apple II, and then here's an old Mac.
What kind of camera are you using for your webcam?
This is a Sony A6100. So it's basically just it's not a video camera. It's a regular camera, just in video mode.
Yeah, I assumed.
The key is to get a nice lens for it. And that's what I got here. I'm probably going to host like a workshop for other teachers. Say, if you want to do what this is, here's like, of course, it has to do with how much you want to spend on it. You can spend a little, or you can spend a lot.
Yeah, this is definitely the best I've seen.
Oh, I try. It gives me a lot of pleasure to make something that you appreciate. If you're curious, I have, let's see. So the camera's there, right? But occasionally I look over there because that's where my Zoom screen actually is. Right? The camera's there, but there's no screen underneath it. So right there is where I see all the icons for you. And then over here, you can't see, but occasionally I look over here. That's where the chat is, and that's the computer that's actually doing the Zoom session. So there's just a second. There's just a second display up here that's showing the grid of icons, and then down over here is the actual computer doing the work. And then I got a laptop in front of me. So when I show the laptop mode, you're looking at the laptop that's right in front of me. So I look down at that one. And then the iPad is over there. There's another iPad behind that one that has my notes. So usually when I give you an example, I've already worked out the example on another iPad, and I just look at that one. And then
so is that about 4 monitors in total if you count the iPad?
I'm not done yet. And then over here is a display that's showing you all the camera inputs going into my switch. I'm not using software to do switching. I'm not using like OBS or vMix to do switching. I'm using a hardware switcher by Blackmagic Design. Because
is that like a KVM switch? I think that's what they're called.
Kind of, but it's a professional video switcher.
Oh, okay.
The reason for that was I have so many inputs going in. I got laptop, iPad. What else? I got a camera, and I have this one that you see beginning. That's another computer that's running. So I have so many inputs coming in that the poor computer was just overloaded with the number of inputs coming in. So I got that video switcher to offload that processing onto something else. And so there's actually 2 of those. There's one that's doing the primary Zoom one, and there's a second one that's doing just the switching for YouTube. So on YouTube, they see what you're seeing right now, but they also see my picture superimposed over the background. And then I can switch that on and off just for them, and I can mute them so that if we talk about something private, the YouTube channel gets cut out. And so there's a separate switcher just for that.
That's awesome.
So I have 1, 2, 3, 4, 5, 6 screens, plus the screen on my camera. That doesn't really count. And then also the last screen I got is I just have my regular desktop computer on here. So when I'm not doing classes, this is just my regular surf Reddit.
Me too.
Yeah, computer. And so I don't have that one on right now. That one's just devoted strictly for kind of like personal use. And then my desk goes up and down as well. So I'm standing up right now, and then all the video equipment's in front of me. And then when I just end the class, I lower it back down to sitting height, and then I don't have a camera staring at me for the rest of the day.
That's
Like
convenient.
it's up there when I'm sitting down. So it's kind of nice. It gets out of my visual range. So I stand up to do the classes, and I sit down when I'm done. So someday I'll like fire up those old computers and show them to you. Yes, there's an oscilloscope there, old hard drives there.
I've seen some people on YouTube do some like cool math, like they do like 3D graphing on oscilloscopes. I'm not sure if you've done any sort of stuff like that.
I've seen those too. I don't know if these digital oscilloscopes can do those. I know the old analog ones can. And then over here I've got abacus, slide rules, and then I got a microscope there, and just other assorted books. So again, I'll give you a complete tour of this someday. But this is sort of like the set is little facets of my interests and personality.
I like it.
And there's also a table right down there, of course. That's where my son sits when he has to do homework. All right. Now we've talked enough. Oh, YouTube people say hello from Australia. And well, we reached the end of today. What does this mean? You need to have a specific type. I don't understand that message.
I think he was talking about the oscilloscope.
Oh, yeah. Yeah, I tried. I watched some of those videos on YouTube, and they said if you want to try this out yourself, all you have to do is like download this audio file and plug it into your oscilloscope, and then the pattern will appear on the screen. And I tried it, and it didn't quite work. And so either I don't have it set correctly, there's some adjustments you have to make, or the digital oscilloscopes just can't do it as well as the analog ones can. So my, someday I might go and buy one of those analog ones. The problem is they're just big, right? The front of them is the same size. You got a screen and some controls. But the digital ones are only about 6 inches deep, and the analog ones are like 1.5 feet deep. So then the question becomes, where do I put that thing when I'm not using it?
Yeah.
My dad used to have one that was, I think, at least 2 feet tall.
Oh my goodness.
Oh man.
And there were some old ones that you could get that had pluggable modules. So you plugged in the screen module, and you plugged in the module for if you wanted to decode audio signals, you get one for those. And you wanted to decode video signals, you get one of those. And you basically plugged in the different modules. And that could make a really big oscilloscope. But most of them are compact desktop models.
So do you collect the Apple computers that are in the background, or are those just your old machines?
No, I kind of collect them because I grew up with them. Actually, these are not the ones that I had when I was a kid. These are the ones I wanted to have, but I couldn't afford. So I had an.
Oh, yeah, they were like $1,500 back then, right?
Oh, more than that, like $3,000, which is like $6,000 in today's money. So yeah, my family couldn't afford them. So I had an Apple II when I was growing up, and those again were fairly expensive. But I wanted an Apple II GS. So I bought one. Now, like a year ago, during the pandemic. And then this Mac over here, I had a Mac Plus when I went to college. This is an SE30. This is the one I wanted to have. It was super expensive. This was like a $5,000 computer when it came out.
Not as much now.
No, not as much now. And they usually don't work.
It's a collector's item.
Yeah, they usually don't work either, so you have to fix them.
There's a YouTube channel that I watch called the 8-Bit Guy.
Oh, yes.
He does he does restorations on those kinds of things. So always crazy to watch him do the retro braiding.
Oh, I haven't done that yet. I haven't really. This one's still pretty good color. That one's still pretty good color. I have an Apple IIe over here. That's very similar to the one I had when I was a kid. That one's all yellow. So eventually, I may get around to retrobrighting that. But the downside of retrobrighting, which is to remove the yellowness, is that it makes the plastic more brittle. So you actually deteriorate it in order to make it more aesthetically pleasing. So it's kind of like a trade-off.
Yeah. He doesn't talk about that part.
You have to like remove a film from the display to do that.
So what happens is the plastics are made from ABS, which is the same kind of plastic used in Legos, but they've added a chemical to make it more heat resistant, fire resistant. You know, because you don't want your computer emitting noxious fumes if it were to ever
You guys are
catch fire.
talking about the outer frame.
Yeah, and so it's that fireproofing stuff that makes the plastic change color over the years. And so what retrobrighting does is it just chemically alters the composition of the plastic so that it removes the yellow color. It doesn't really bleach it out, although you typically use hydrogen peroxide. But it seeps into the plastic and it changes the chemical composition. But the downside is it now makes the plastic more brittle, so it's easier to break. And it will also eventually reverse itself. The retrobrighting will eventually undo itself, and it'll turn yellow again. So you just have to retrobrite it again. And every time you do it, you make it more brittle. So it's kind of like, what do I do? Do I make it look like the original color at the expense of making it more brittle, or do I just leave it yellow? And so I've just elected to leave it yellow for now, because I don't really use that one. I have the Apple II GS, which is a much more fun machine to use.
So that's why all old machines look older than they actually are supposed to look.
Yeah, I even have, I had just, you can't see it's off the screen here. I had an old laser printer. And by old, I mean it was like 10 years old. And it had already started to yellow. But because some of the panels have that fireproofing on it and some don't, some parts of it turn yellow and some of the parts of it remain white. And with these old computers, you can also see it on the keyboard. Some of the keys have that fireproofing on it and some don't. Like the spacebar typically does have it, and the letter keys don't have it. So the letter keys end up being kind of the original color, and the spacebar turns this ugly yellow. So you have to retrobrite just that one. Anyway, so I ended up talking about all this stuff.
Sorry.
That's all right. That's all right. We got plenty of time. Yeah. So someone's here. The 8-bit guy is genius. Yeah, I watch some of his stuff. I also watch this guy called Branches Creations. He does restorations of old Macs, and his is fun because he gets a microscope with a camera on it. You can actually see him doing the individual soldering work. And I watch his, and I pick up all these tips on how to restore these things. Because when I get that, it doesn't work. Because the electronic parts have deteriorated over the 30 years. So you have to replace some of the parts. And so, I don't know, can you? Nope, you can't see it. But right down there, right off the screen, is soldering stations for me to do the work on it.
Oh, that's cool.
Anyway, like I said, I can talk more about it later. So why don't we wrap this up? Have a good day, everyone. I will see you on Monday at 9:30. Good to have you here. Take care. Have a good weekend. For some of you, you're in my other class, my Tuesday, Thursday class, so I will see you then at 9:30 tomorrow. For those of you who are watching on YouTube, also I have the other class, the C programming class, Tuesdays and Thursdays at 9:30, and so you can watch the live stream there as well. So have a great day.
Sorry, my AirPods died when I was trying to respond to you, but I cut out, so thank you.
You're welcome. Have a great day.
See, what is the where do I find the YouTube channel?
You could search for my name,
Mhm.
or you could search for Prof B Brown, PROF BBROWN.
Okay.
Did you find it?
Not yet.
Funny when I search
There it is.
when I search for my
There it
name,
is.
it comes right up. But that may be because Google, who owns YouTube, knows that I search for my name all the time.
Yeah. Okay. Cool.
Oh yeah, I'm not the. Oh, you have to click on search instead for Prof B Brown.
Yeah. Well, I searched for Prof space B Brown. That didn't show up. But when I searched for it all one word, it showed
Got
up
it.
just fine. Cool. I would be interested to listen in on the C programming lectures.
Glad to have you.
Oh yeah, I noticed something earlier. You had your Gmail. Is it actually bb@gmail.com?
No.
Oh, okay, I was gonna say that's pretty rare.
No.
Characters.
No, I made up those email addresses.
Hmm.
Because it used to be, I would just do that particular page just for my class on Zoom, and it was like, oh, if my students know my email address, no problem. But now I have a global audience, and so I had to change those. At first,
okay.
at first I
That
just
makes
blurred
sense.
them out, and I went, well, that looks kind of gross. so I just put fake addresses there. So somebody named BB is going to get some email.
Just like whoever had the phone number that was in that song.
867-5309.
Mhm.
There's some web articles about the business that owns that number.
Hmm.
They apparently have a lot of fun with it. It's not like they're totally annoyed. They have fun with people who call that number.
Yeah.
All right. I'll say take care again one last time. So, have a good day, everyone.
Yeah.
You too. It was
See you
good talking with
either
you.
tomorrow or Monday.
Mhm.
Bye-bye.
Bye.
And YouTube folks, thanks for tuning in. I'll see you either tomorrow for my C programming class or on Monday for this class. Have a great day. Bye-bye.